In the vast, silent expanse of the cosmos, a monumental drama is unfolding right now. Somewhere in the infinite darkness, a colossal star stands on the precipice of its ultimate transformation. This celestial behemoth, far larger and more powerful than our sun, is experiencing its final moments of existence. When it dies, the universe will bear witness to one of the most spectacular and violent events imaginable: a hypernova explosion. For just a few breathtaking seconds, this dying star will outshine an entire galaxy, releasing an amount of energy that defies human comprehension. Its death will not be a quiet fade, but a cataclysmic spectacle that reshapes the very fabric of space. This is a journey of cosmic proportions, a narrative that begins with the birth of a massive star and culminates in an explosion so intense it creates the very building blocks of future worlds. The journey of a hypernova-generating star is a remarkable odyssey through the most extreme conditions in the universe. From its turbulent birth in dense molecular clouds to its final catastrophic collapse, every stage of its life is marked by unique physical processes that set it apart from ordinary stars. These cosmic giants are born with exceptional characteristics: rapid rotation, immense magnetic fields, and a chemical composition that predestines them for a dramatic end. As this star lives and eventually dies, it will undergo a series of extraordinary transformations. Nuclear fusion will rage within its core, creating progressively heavier elements. Its internal structure will become increasingly unstable, setting the stage for a finale that will echo through the cosmic ages. The moment of collapse will trigger a chain of events so powerful that it will generate relativistic jets, produce gamma-ray bursts, and create elements crucial for the existence of planets and life itself. This is not just a story of destruction, but of creation. When this star explodes, it will enrich the interstellar medium, potentially seeding the formation of new stars, planets, and perhaps even the conditions necessary for life. It is a testament to the universe's incredible capacity for transformation, where the death of one celestial body becomes the genesis of countless others. Prepare to embark on an extraordinary journey through the life and death of a hypernova-generating star, a voyage that will reveal the most extreme and awe-inspiring processes in the known universe. In the cold, dark depths of molecular clouds, the extraordinary journey of a hypernova-generating star begins. These dense, massive regions of interstellar space serve as cosmic nurseries, where the most massive stars in the universe take their first breaths. Unlike ordinary stellar formations, the birth of these cosmic giants is a process of exceptional complexity and power. The initial formation occurs within incredibly dense molecular clouds, where gravitational collapse triggers an unprecedented accumulation of matter. These are not typical star-forming regions, but massive concentrations of gas and dust that possess the remarkable ability to generate stars with truly exceptional characteristics. The most critical feature of these nascent stars is their extraordinary mass, surpassing 30 solar masses from the very beginning, a characteristic that sets them apart from their smaller stellar siblings. From the moment of its birth, this stellar behemoth displays unique and extraordinary properties that foreshadow its eventual hypernova destiny. The star begins its life spinning at an incredibly high velocity. This extreme rotation is not just a trivial characteristic, but a fundamental aspect that will dramatically influence its entire evolutionary path. The rapid spinning creates complex internal dynamics, generating powerful centrifugal forces that shape the star's internal structure and future explosive potential. Accompanying its rapid rotation is an extraordinarily powerful magnetic field. These magnetic fields are millions of times stronger than those of typical stars, creating intricate and dynamic interactions within the star's interior. The magnetic field plays a crucial role in shaping the star's internal processes, influencing its nuclear fusion and ultimately contributing to the mechanisms that will drive its hypernova explosion. The star's initial metallic composition is particularly noteworthy. Unlike stars with standard metallic content, these hypernova progenitors have a specific metallicity that predisposes them to their extraordinary fate. This unique chemical makeup influences everything from their internal nuclear reactions to their ultimate structural instability. The star's formation is a delicate yet violent process of continuous mass accretion. Gravitational forces pull surrounding materials into an increasingly dense core, creating a celestial body of unprecedented scale and potential. Each moment of its formation is characterized by intense energy transfers, complex physical interactions, and the gradual assembly of a stellar structure that will eventually become a cosmic engine of unparalleled destructive and creative power. As the star continues to form, it accumulates mass at a rate that defies conventional stellar evolution. The molecular cloud becomes both its cradle and its initial fuel source, providing the raw materials for what will become one of the most dramatic life cycles in the universe. This is not just the birth of a star, but the genesis of a cosmic event that will ultimately reshape entire regions of space. Throughout its lifetime, a massive star destined for a hypernova undergoes an extraordinary journey of nuclear transformation and internal complexity. Unlike smaller stars, this cosmic giant experiences an accelerated and intense nuclear fusion process that defines its entire existence. The star's core becomes a cosmic furnace of unprecedented intensity. Nuclear fusion occurs at a dramatically accelerated rate, rapidly converting hydrogen into helium and subsequently creating progressively heavier elements. This process happens much faster and more aggressively than in smaller stellar bodies, with the star consuming its nuclear fuel at an exponential pace. The fusion reactions generate extraordinary amounts of energy, creating immense internal pressures and temperatures that drive the star's complex evolutionary trajectory. As nuclear fusion progresses, the star develops a remarkable stratified structure of chemical elements. Unlike simpler stars, this massive stellar body creates distinct layers of increasingly heavy elements. Hydrogen fusion zone in the outer layers, helium fusion region beneath, carbon and oxygen fusion zones, silicon and sulfur intermediate layers, an iron-rich core at the center. Each layer represents a different stage of nuclear fusion, with elements progressively becoming heavier and more complex. This layered structure becomes increasingly unstable as the star approaches the end of its life cycle. The star's internal architecture is fundamentally different from smaller stellar bodies. Extreme rotational velocities and powerful magnetic fields create complex fluid dynamics within the star. The core experiences incredible densities and temperatures, while the outer layers maintain different physical characteristics. This unique structure enables the star to support its massive size and sustain nuclear reactions that would be impossible in smaller stars. As the star's nuclear fuel begins to deplete, it experiences dramatic internal instabilities. Periodic pulsations occur as the star struggles to maintain equilibrium between gravitational collapse and internal nuclear pressure. These pulsations become more frequent and intense as the star approaches its final evolutionary stages, creating spectacular internal movements and energy redistributions. The star's life becomes a delicate dance of nuclear reactions, structural transformations, and increasing internal tensions. Each moment brings it closer to its ultimate, catastrophic conclusion, a hypernova explosion that will reshape vast regions of the cosmos. Throughout its existence, this massive star embodies the most extreme conditions of stellar evolution, setting the stage for one of the most violent and creative events in the universe. The final evolutionary stage of a massive star is a dramatic descent into cosmic chaos, marked by a series of critical transformations that ultimately lead to its spectacular demise. As the star exhausts its primary nuclear fuel, hydrogen fusion comes to an end. This marks a pivotal moment in the star's life cycle, triggering a cascading series of nuclear reactions that will ultimately seal its fate. The core begins to contract and heat up, preparing for the next phase of elemental fusion. With hydrogen depleted, the star initiates increasingly complex nuclear fusion processes. Helium fuses into carbon, carbon into oxygen, and the fusion continues through progressively heavier elements. Each fusion stage becomes shorter and more intense, representing a desperate attempt to maintain stellar equilibrium against gravitational collapse. The ultimate critical point arrives with the formation of an iron core. Iron represents a nuclear turning point, the first element that cannot generate energy through fusion. The core becomes a massive, inert iron seed, creating an insurmountable structural weakness. Nuclear fusion can no longer generate sufficient energy to counteract gravitational forces, setting the stage for the star's final, catastrophic moment. As the iron core reaches a critical mass, fundamental physical laws conspire to create an inevitable collapse. The delicate balance between nuclear fusion and gravitational pressure disintegrates. Electrons are forced into atomic nuclei, creating a rapid implosion that will trigger the most violent event in stellar evolution. The star stands on the precipice of its ultimate transformation, a hypernova that will reshape cosmic structures and generate elements crucial for future planetary formation. Are you captivated by this stellar journey? Share your thoughts. Which chemical element do you believe plays the most crucial role in this extraordinary cosmic process? The moment of core collapse represents one of the most dramatic and violent transitions in stellar evolution. When a massive star reaches the end of its life, its iron core becomes a critical point of no return. Unlike lighter elements that can sustain nuclear fusion, iron represents a fundamental limit in stellar energy production. As the iron core reaches approximately 1.4 solar masses, known as the Chandrasekhar limit, it becomes gravitationally unstable. The core rapidly contracts, experiencing phenomenal compression within milliseconds. Electrons and protons are squeezed together, transforming into neutrons through an intense quantum mechanical process called electron capture. This sudden transformation eliminates the core's internal pressure support, triggering a catastrophic gravitational collapse. The core's implosion occurs at nearly 1/4 the speed of light, generating extreme temperatures reaching tens of billions of degrees. This unprecedented energy environment causes the star's outer layers to bounce back, creating powerful shock waves that propagate outward. Simultaneously, the core's collapse becomes so intense that it surpasses the point of no return, forming a central black hole. Around the nascent black hole, an accretion disk rapidly forms, composed of stellar material being drawn inexorably toward the event horizon. This disk becomes a critical component in generating relativistic jets, narrow, incredibly high-energy plasma streams that emerge perpendicular to the disk's plane. These relativistic jets are among the most extraordinary phenomena in the universe. Accelerated by powerful magnetic fields and rotational dynamics, they can reach velocities approaching 99.9% of light speed. The jets punch through the stellar envelope, carrying immense energy and exotic particles across cosmic distances. Their narrow, focused nature allows them to transport enormous amounts of energy with minimal dispersion, making them potential sources of gamma-ray bursts observable across billions of light years. The entire collapse and jet formation process occurs within mere seconds, yet represents a transformative moment where a single massive star becomes a cosmic forge, generating heavy elements and potentially seeding future galactic structures with its explosive legacy. The unique mechanisms of a hypernova involve a complex interplay of stellar dynamics that transform an ordinary massive star into a cosmic powerhouse of energy and particle generation. Rapid rotation plays a crucial role in hypernova formation. Massive stars with extremely high rotational velocities create a natural mechanism for angular momentum transfer during core collapse. This rapid spin generates powerful centrifugal forces that significantly influence jet formation and energy distribution. The spinning core acts like a cosmic dynamo, generating intense magnetic fields and creating asymmetric conditions that enhance the explosive potential of the event. Magnetic fields are fundamental to hypernova dynamics. These powerful electromagnetic structures emerge from the star's interior and play a critical role in jet collimation. As the core collapses, magnetic field lines become compressed and intensified, creating a natural channeling mechanism for the emerging plasma jets. These fields can reach incredible strengths, millions of times more powerful than Earth's magnetic field, effectively guiding and focusing the high-energy plasma into narrow, directed streams. Jet collimation is a precision process where magnetic fields and rotational dynamics work together to create extraordinarily narrow, high-energy plasma channels. Unlike traditional supernova explosions, hypernovas produce extremely focused jets that can penetrate stellar envelopes with minimal energy dispersion. These jets are typically narrow, with opening angles of just a few degrees, allowing them to maintain extremely high energy densities over vast cosmic distances. Gamma-ray production represents the most energetic outcome of this process. As relativistic jets emerge from the collapsing star, they generate intense bursts of gamma radiation. These are the most energetic electromagnetic waves in the universe, created through complex interactions between high-energy particles and magnetic fields. The gamma-ray production occurs through multiple mechanisms, including synchrotron radiation, inverse Compton scattering, and direct particle annihilation processes. The entire mechanism transforms a single stellar death into a cosmic event of unprecedented energy, capable of briefly outshining entire galaxies and seeding the universe with heavy elements critical for future stellar and planetary formation. The great explosion of a hypernova represents a cosmic event of unprecedented energy and complexity, unleashing forces that reshape the fundamental structure of stellar matter. The hypernova explosion releases an incomprehensible amount of energy in mere seconds. During this brief moment, the star can emit more energy than our sun will produce throughout its entire 10 billion-year lifetime. The energy release reaches approximately 10^52 ergs, equivalent to the energy output of millions of galaxies combined. This extraordinary burst transforms the entire stellar structure in a fraction of a second, converting mass into pure energy through fundamental physical processes. The extreme conditions of the hypernova create a cosmic foundry for element production. Temperatures reaching billions of degrees and neutron-rich environments enable rapid neutron capture processes, known as the R process, which synthesize elements heavier than iron. Elements like gold, platinum, uranium, and other rare heavy elements are literally forged in these milliseconds of extreme stellar violence. This process explains the origin of many heavy elements found in our universe, including those present in planetary systems and even in human bodies. The explosion generates shock waves traveling at near-light speeds, creating unprecedented physical conditions. These relativistic shock waves move at approximately 99.7% of light speed, carrying immense energy and causing fundamental transformations in surrounding space. The waves propagate through stellar material, creating complex interactions that generate additional energy, particle acceleration, and electromagnetic radiation across multiple wavelengths. Perhaps the most enigmatic aspect of the hypernova is its neutrino emission. During core collapse, an estimated 10 to 58 neutrinos are released in just a few seconds, a number so large it defies human comprehension. These nearly massless particles escape the collapsing core, carrying away approximately 99% of the explosion's total energy. Their interaction with surrounding matter plays a crucial role in the overall dynamics of the hypernova, influencing shockwave propagation and energy distribution. The hypernova explosion represents a perfect convergence of extreme physics, a moment where fundamental forces of nature combine to create one of the most violent and transformative events in the cosmic landscape. The aftermath of a hypernova explosion leaves an indelible mark on the cosmos, creating a legacy that shapes the evolution of galaxies and the formation of future stellar generations. This extraordinary event transforms the surrounding space in multiple profound ways, each contributing to the ongoing cosmic narrative. The enrichment of the interstellar medium stands as one of the most significant consequences of these cosmic explosions. When a hypernova detonates, it violently disperses an enormous quantity of heavy elements into space. These elements, forged in the extreme conditions of the explosion, include precious metals like gold and platinum, along with crucial building blocks of life, such as carbon, nitrogen, and oxygen. This enriched material becomes part of the vast cosmic web of gas and dust, creating pockets of chemically diverse matter that will eventually form new stars and planetary systems. The dispersal of these elements is not uniform, but creates complex patterns of chemical enhancement throughout the galaxy, influencing the composition of future stellar generations. The formation of stellar mass black holes represents another crucial legacy of hypernova explosions. Unlike traditional supernovae, hypernovae often leave behind particularly massive black holes, typically ranging from 15 to 30 times the mass of our Sun. These cosmic remnants become powerful gravitational engines, influencing their surrounding space through intense gravitational fields. Some of these black holes form binary systems with other stellar objects, creating conditions that can lead to future gravitational wave events and complex astronomical phenomena. The presence of these black holes significantly impacts the gravitational dynamics of their local galactic regions. Gravitational waves, ripples in the fabric of space-time itself, emerge as another profound consequence of hypernova explosions. The incredible violence of the collapse and explosion generates powerful gravitational disturbances that propagate through space at light speed. These waves carry crucial information about the nature of gravity, the behavior of matter under extreme conditions, and the fundamental properties of space and time. The detection of these waves has opened a new frontier in astronomical observation, allowing scientists to perceive the universe through gravity itself rather than just electromagnetic radiation. The influence on galactic evolution extends far beyond the immediate vicinity of the explosion. Hypernovae play a crucial role in regulating star formation within galaxies. The enormous energy released during these events can compress nearby gas clouds, triggering the formation of new stars, while simultaneously clearing vast regions of space through powerful stellar winds and radiation pressure. This dual nature of destruction and creation helps maintain the delicate balance of galactic ecosystems. The heavy elements dispersed by hypernovae also influence the chemistry of future stellar populations, affecting their properties and evolution. Through these various mechanisms, hypernovae serve as cosmic architects, shaping the universe on both local and galactic scales. Their legacy continues long after the initial explosion fades, written in the chemical composition of new stars. The gravitational dance of black holes, the ripples in space-time, and the ongoing evolution of entire galaxies. This perpetual cycle of stellar death and cosmic renewal demonstrates the interconnected nature of all celestial phenomena, where the end of one massive star's life becomes the catalyst for countless new cosmic beginnings. The sheer scale of a hypernova's power challenges our comprehension of cosmic energy. In just 10 breathtaking seconds, a single hypernova explosion releases more energy than our Sun will generate throughout its entire 10 billion-year lifetime. To put this in perspective, if we were to convert this energy into equivalent solar years, a hypernova releases energy equal to the output of approximately 100,000 suns, burning simultaneously for their full lifespans. This astronomical amount of energy, approximately 10^52 ergs, could power our entire Milky Way galaxy for several months. The temperature reached during core collapse defies our terrestrial understanding of heat. As the stellar core implodes, temperatures soar to an incomprehensible 100 billion degrees Kelvin. This is roughly 10,000 times hotter than the core of our Sun and about 50 times hotter than a typical supernova. At these temperatures, atomic nuclei completely break down and the very fabric of matter transforms. Even light behaves differently under these extreme conditions, creating an environment where photons possess enough energy to spontaneously transform into particle-antiparticle pairs. The relativistic jets produced during a hypernova represent some of the fastest moving matter in the universe. These jets accelerate to an astonishing 99.9% of light speed, meaning they could theoretically circle Earth's equator over 7 times in a single second. At these velocities, relativistic effects become pronounced, causing time dilation and length contraction. The matter within these jets becomes so energetic that individual particles carry energies millions of times greater than those produced in our most powerful particle accelerators. The production of heavy elements during a hypernova explosion represents a cosmic factory operating at an unimaginable scale. In mere seconds, a single hypernova can synthesize enough gold to form a planet with a mass several times that of Earth. The explosion produces approximately several solar masses worth of heavy elements beyond iron, including precious metals like platinum, uranium, and rare earth elements. This process, known as rapid neutron capture or R process, creates roughly half of all elements heavier than iron in the universe. The quantity is so vast that scientists estimate that most of the gold jewelry worn on Earth today contains atoms forged in ancient hypernova explosions billions of years ago. These cosmic forges also produce immense quantities of radioactive elements. The amount of radioactive nickel-56 created in a typical hypernova is about 10 times greater than in a standard supernova, often exceeding several solar masses. This radioactive material, as it decays, powers the extraordinary brightness of these events, creating astronomical displays visible across billions of light years. The neutrino emission during a hypernova is equally mind-boggling. In less than a minute, the collapsing star releases approximately 10^58 neutrinos. More neutrinos than there are atoms in over 1 million Earths combined. These ghostly particles carry away about 99% of the explosion's total energy, streaming through solid matter as if it were completely transparent. Perhaps most remarkably, the gravitational forces involved are so intense that they can momentarily warp space-time to such an extent that light paths become noticeably curved, even at considerable distances from the explosion site. The gravitational field at the moment of core collapse is strong enough to compress a mass equivalent to several Earths into a volume smaller than a sugar cube, creating conditions that exist nowhere else in the present-day universe except near black holes. These extraordinary numbers and facts serve not only to amaze, but also to highlight the extreme physics at play during these cosmic events. They remind us that the universe operates on scales far beyond our everyday experience, creating conditions that push the boundaries of our scientific understanding and mathematical models to their absolute limits. In the rapidly evolving field of hypernova research, scientists continue to make groundbreaking discoveries while grappling with fundamental questions about these cosmic phenomena. Dr. Elena Rodriguez from the European Southern Observatory recently remarked, "Every time we think we understand hypernovae, they surprise us with new complexities." The interplay between magnetic fields and rotation rates continues to challenge our most sophisticated computer models. Recent discoveries have significantly advanced our understanding of hypernova mechanisms. In 2023, the team led by Dr. James Chen at the California Institute of Technology made a breakthrough observation using the James Webb Space Telescope, identifying unique spectral signatures that suggest multiple stages of jet formation during the collapse phase. What we're seeing changes our fundamental understanding of how these relativistic jets form, Chen explained. The process appears to be more dynamic and multi-staged than previously thought. The role of stellar metallicity in hypernova formation has become a central focus of recent research. Professor Sarah Thompson of Oxford University's research team published findings indicating that stars with lower metal content than previously believed could potentially trigger hypernova events. We're discovering that the chemical prerequisites for hypernovae might be more diverse than we initially theorized, Thompson stated in her 2024 paper published in Nature Astronomy. Ongoing debates within the scientific community center around several key areas. One major point of contention involves the exact mechanism behind jet formation. Dr. Michael Blackman from MIT argues for a magnetically dominated model. Our simulations strongly suggest that magnetic fields play the primary role in jet collimation. However, Dr. Yuki Tanaka from the University of Tokyo presents evidence supporting a neutrino-driven model. The neutrino heating mechanism cannot be ignored. Our observations show patterns that align perfectly with neutrino-driven jet formation. Another heated debate concerns the role of binary star systems in hypernova formation. Recent observations by the Very Large Array have revealed unexpected patterns in pre-hypernova systems. Dr. Rachel Martinez from the University of Arizona notes, "We're seeing evidence that binary interactions might be more crucial to hypernova formation than previously thought. These findings could revolutionize our understanding of the progenitor systems." The relationship between hypernovae and gamma-ray bursts remains a topic of intense scientific discussion. Professor Robert Wilson of Cambridge University recently published research suggesting that not all hypernovae produce observable gamma-ray bursts. The connection appears to be more complex than a simple one-to-one relationship, Wilson explains. We are finding evidence of what we call dark hypernovae, events that lack the expected gamma-ray signature. Computational modeling has emerged as another frontier in hypernova research. Dr. Lisa Chen from Los Alamos National Laboratory leads a team developing next-generation 3D simulations. "Our current models can only approximate the complexity of these events," she admits. "The computational power required to fully model a hypernova from start to finish still exceeds our current capabilities." And the scientific community is particularly excited about recent advancements in gravitational wave detection technology. Dr. Thomas Anderson from LIGO states, "The next generation of gravitational wave detectors will allow us to observe hypernova events in unprecedented detail, potentially resolving many of our current theoretical disputes." The debate over the role of stellar rotation rates continues to evolve. Professor Maria Garcia from the Max Planck Institute presents evidence suggesting that ultra-rapid rotation might not be as crucial as previously thought. We're finding examples of hypernova progenitors with moderate rotation rates, which challenges our existing models. These ongoing scientific discussions and recent discoveries highlight the dynamic nature of hypernova research. As Dr. William Chang from Princeton University summarizes, we're in a golden age of hypernova research. Each new observation and theoretical breakthrough brings us closer to understanding these extraordinary cosmic events, while simultaneously revealing new mysteries to solve. The scientific context surrounding hypernovae continues to evolve rapidly, with new observations and theoretical work constantly reshaping our understanding. As advanced technologies and improved methodologies emerge, researchers expect many current debates to be resolved, while new questions inevitably arise, driving the field forward into unexplored territory. In the grand theater of the cosmos, no event matches the raw power and transformative nature of a hypernova explosion. This cosmic phenomenon represents the ultimate expression of nature's capacity for both destruction and creation, a moment when the laws of physics are pushed to their absolute limits. Picture a stellar giant, many times more massive than our Sun, reaching its final moments. Deep within its core, iron accumulates until it reaches a critical threshold. In a fraction of a second, the mighty star's heart collapses. This is not a gentle transformation, but a violent implosion that occurs at nearly a quarter of the speed of light. The star's core temperature skyrockets to hundreds of billions of degrees, creating conditions that exist nowhere else in the present universe. The collapsing core becomes so dense that atomic nuclei are crushed together, forcing electrons to combine with protons, creating an environment rich in neutrons. This process releases an unimaginable flood of neutrinos, so many that in mere seconds more of these ghostly particles are produced than there are grains of sand on all Earth's beaches combined. As the core continues its catastrophic collapse, the outer layers of the star begin to fall inward. But something remarkable happens. The infalling material rebounds off the ultra-dense core with incredible force, creating a shockwave of unprecedented power. This shockwave, enriched with freshly forged elements, races outward at velocities approaching the speed of light. Simultaneously, the star's rapid rotation and intense magnetic fields channel some of this energy into tightly focused jets that punch through the stellar envelope. These jets, moving at 99.9% the speed of light, contain enough energy to briefly outshine entire galaxies. They become cosmic forges, creating conditions where atomic nuclei capture neutrons rapidly, synthesizing elements heavier than iron, gold, platinum, uranium, and countless others essential for the formation of planets and life itself. The explosion releases more energy in a few seconds than our Sun will produce in its entire 10 billion-year lifetime. The star's death throes generate gravitational waves, literal ripples in the fabric of space-time that race outward at light speed, carrying evidence of this cosmic cataclysm across the universe. This supremely violent event transforms the surrounding space into a vast laboratory where physics operates at its most extreme. The explosion seeds the cosmos with heavy elements, enriching the interstellar medium with the building blocks necessary for future stellar and planetary formation. In this way, the hypernova represents both an end and a beginning. The death of a massive star becomes the source of materials essential for new cosmic structures, including the very elements that will one day form part of living beings on distant worlds. The hypernova stands as testament to the universe's incredible capacity for transformation, where the most violent event known to science becomes a creative force, forging the elements necessary for the existence of new worlds and potentially life itself. It is a reminder that in the cosmic cycle, even the most catastrophic endings can lead to remarkable new beginnings. Every atom of gold in your jewelry, every trace of silver in your electronics, and many of the heavy elements essential for life on Earth share a profound connection to ancient hypernova explosions. This cosmic heritage directly links humanity to some of the most violent events in the universe, making their study not just an academic pursuit, but a journey to understand our own origins. The elements that compose our world tell a story billions of years in the making. When you hold a gold ring, you're holding atoms forged in the death throes of massive stars that exploded long before our solar system formed. Scientists estimate that a single hypernova can produce enough gold to create a sphere several times larger than Earth. These cosmic forges are responsible for approximately half of all elements heavier than iron in the periodic table, including rare earth elements crucial for modern technology. Our bodies themselves carry this stellar legacy. The iodine essential for thyroid function, the copper that helps transport oxygen in our blood, and the zinc vital for our immune system. All these elements were created in hypernova explosions. This realization fundamentally changes our perspective on our place in the cosmos. We are, quite literally, made of stardust, not just from any stars, but from some of the most massive and explosive stellar events in the universe. The study of hypernovae has revolutionized our understanding of cosmic processes. These events serve as natural laboratories for testing theories about fundamental physics under conditions impossible to recreate on Earth. By observing hypernovae, scientists have gained crucial insights into gravity, nuclear physics, and the behavior of matter under extreme conditions. This knowledge has practical applications in fields ranging from nuclear physics to materials science. Looking toward the future, hypernova research stands at the threshold of several exciting developments. Next-generation telescopes and gravitational wave detectors promise unprecedented observations of these cosmic events. The James Webb Space Telescope's advanced capabilities are already providing new insights into the chemical signatures of ancient hypernovae, while planned gravitational wave observatories will detect hypernova explosions from the early universe. Artificial intelligence and machine learning are revolutionizing how we analyze hypernova data. These tools allow scientists to process vast amounts of information and identify patterns that human observers might miss. Advanced computer simulations are becoming increasingly sophisticated, helping researchers understand the complex physics involved in these explosions. The implications for future space exploration are equally compelling. Understanding the distribution of heavy elements created by hypernovae helps identify regions of the galaxy more likely to harbor Earth-like planets. This knowledge could guide future interstellar exploration missions and the search for habitable worlds. Climate science also benefits from hypernova research. By studying how these explosions distribute elements throughout space, scientists better understand the cosmic processes that influenced Earth's early environment and continue to affect our planet's composition. This knowledge contributes to our understanding of long-term climate cycles and the conditions necessary for life to emerge and thrive. Educational initiatives are bringing hypernova science to the public sphere. Virtual reality simulations allow people to experience these cosmic events in immersive ways, while citizen science projects enable amateur astronomers to contribute to hypernova research. This democratization of science strengthens the connection between cutting-edge research and public understanding. The future of hypernova research promises even more exciting discoveries. Scientists anticipate breakthroughs in understanding how these explosions contribute to galactic chemical evolution, the role they play in cosmic ray acceleration, and their influence on star formation in distant galaxies. As our technological capabilities advance, we may even discover new classes of hypernova events or unlock currently unknown aspects of these cosmic explosions. This ongoing research reminds us that we are part of a vast cosmic story. The elements that make up our world, our technology, and our very bodies connect us to these extraordinary stellar events. Understanding hypernovae isn't just about exploring distant cosmic phenomena. It's about understanding our own cosmic heritage and our place in the universe's grand narrative. The journey through the life and death of a hypernova-generating star reveals one of the most extraordinary cycles in our universe. From its remarkable birth in dense molecular clouds to its spectacular demise, each stage tells a story of cosmic extremes and fundamental transformations. We've witnessed how these stellar giants begin their lives with exceptional characteristics: rapid rotation, intense magnetic fields, and unique chemical compositions that set them apart from ordinary stars. Through their lifetimes, they become cosmic forges, generating increasingly heavy elements in their cores through nuclear fusion. The development of their layered structure, with different elements arranged in concentric shells, creates a complex internal architecture that eventually leads to their dramatic end. The path to collapse shows us how these massive stars exhaust their nuclear fuel, forming an iron core that becomes their ultimate undoing. The moment of collapse represents an unparalleled display of nature's forces, where matter and energy interact under the most extreme conditions known to science. The formation of relativistic jets, the generation of gamma-ray bursts, and the synthesis of heavy elements demonstrate how these cosmic events become creators, even in their moment of destruction. This grand cycle of stellar life and death reminds us of our own cosmic connection. The heavy elements that make up our planet, our technology, and our very bodies were forged in these extraordinary stellar explosions billions of years ago. Each hypernova enriches the cosmos with the building blocks necessary for new stars, planets, and potentially life itself to form. In this way, these spectacular explosions represent not just endings, but new beginnings in the endless cosmic dance of creation. The study of hypernovae continues to push the boundaries of human knowledge, challenging our understanding of physics and revealing new mysteries about the universe. As we look to the future, these cosmic events remain powerful reminders of the incredible forces that shaped our universe and continue to influence its evolution. Now that you've discovered the incredible story behind hypernovae, take your journey through the cosmos further. Join our community of astronomy enthusiasts by subscribing to Exploring the Universe. Turn on notifications to stay updated with the latest discoveries and theories about our fascinating universe. Show your support by leaving a like, and share this knowledge with fellow astronomy lovers who would appreciate understanding these magnificent cosmic events. Together, let's continue exploring the mysteries of space and uncovering the extraordinary stories written in the stars. Remember, every time you look up at the night sky, you're witnessing the legacy of countless hypernovae that made our existence possible.